So now we're going to move on to model talk. So previously, when we've been talking about models, we were talking about the mean primarily. So we saw that if you had a group of numbers, you could find the average, and then to figure out how well the mean fit as a model, you could see the sum of squared deviations. You could take x minus x bar and square them, and then you could get variance from that to get kind of an average estimate of how much variance or how much difference there is in your mean compared to the actual data. And then you could take the square root of that to get standard deviation. Well, right now, we're going to kind of expand upon this because previously we were looking at one variable. Now we're going to look at two. So we have looked at standard deviation and variance previously, but now we have scatter plots. We have two variables. We have a variable on the x-axis and a variable on the y-axis. And you might not have completely realized this before, but covariance and variance are actually very similar. So if you were to expand, take the square out and put what that means, just write it out, you get the following. You get that variance is equal to x minus x bar times x minus x bar added up and minus 1. Well, covariance is basically the same thing, but it is with two variables. So this time, what we're going to be doing, what our model is saying, is that as one variable is changing, so is the other one, or it's not. That's the question that we have here. So now we can plot values based on their, we can plot based on the values we have. So we have one that the x value is 0, one this is 2, 1 and 1, 4 and 2, 5 and 5, and 6 and 4. And we can then plot for the average for the x value, so 3.2-ish in this case. And then we can see how far off it is. But we can also do it with the y value. And this is the expansion going from 1 to 2 variables. So now we have it for the y variable as well. And then we can connect them both, and we can see as one value is getting further away from the mean for y, what's going on with the mean for x. So right here you can see that this point is closer to both the average of y and the average of x than this one is. So this is far away from the average of x and far away from the average of y. Now, a correlation of 1 would have these differences be lining up perfectly. So this is a perfect line. It's a perfect correlation of 1, but that doesn't necessarily mean that they're fitting along the means, right? Instead, what it's saying is that the correlation, the differences in the x variables and the differences in the y variables match up. So we're not concerned about just the means, but how much the mean for x is related to changes in the mean for y, or changes from the mean for y. Similarly here, numbers are different, but each one is moving up in a perfect line, proportionately. So the question here is, what would the math look like? Well, let's take a look at covariance. We can see that as there are changes in x, what's going on with the changes in y? Well, here it's up 2 over 2, up 4 over 4, down 2, down 2, down 4, down 4. So they're going proportionately along at the same pace. So if x is equal to 1.5, it is going up, and while y is 1, well, the difference between the means is going down linearly, while the difference is going down linearly for the x values as well. And it's the same with the math here. It's going down linearly as it is going down linearly here. So really what the model for correlation is trying to get at is it's trying to figure out, as there are changes in one value, how much of change is there in another one. And if the changes are perfectly aligned, then the correlation is 1. What we're trying to figure out is how much of an overlap is there.